Okay, so as part of the review for your exam 1, I'm going to go over the sample questions for modules 1 and 3. So this is on module 3, the physical layer. So the first question is, what is the difference between the bit rate and baud rate and how they are related? If the baud rate is of a signal is 4,000 and the number of signal levels is 18, what is the bit rate? Okay, so this is the formula. Bit rate equals baud rate times log k to the base 2. Of course, the difference is the bit rate indicates the number of bits that you can transmit per unit time, so typically represented as bits per second, whereas baud rate is the number of signal level changes that you can have per unit time. So remember in the class we had that slide where we had like, okay, so if this is like one time unit from this in 0 to this, right, say 1 second, we can have 8 slots, right? So these are 8 different time slots. So we can change the voltage levels 8 different times, okay? And each voltage level in this example represented 2 bits because we had 4 voltage levels. So it is 2 bits per voltage level. So the baud rate basically captures the number of time slots that you have per unit time so that you can change the voltage level that many times. Okay, so the baud rate is the number of voltage level changes per unit time. Whereas the bit rate is basically the number of bits you can send per unit time. So that's what is given by this formula. The bit rate is the baud rate times log k to the base 2. This term log k to the base 2 essentially captures the number of bits that you can have per voltage level. So if you put 16 for k, it is log 16 to the base 2 is 4. If you put 8 for k, it is log 8 to the base 2 is 3. 3 voltage levels, sorry, 3 bits per voltage level. If you put 4 for k, it is log 4 to the base 2, it is then 2 bits per voltage level. Okay? So in this example, we have 4,000 for the baud rate and 18 for the number of signal levels. So it is log 18 to the base 2. Also, as I mentioned in class, the number of signal levels are preferably it's multiples of 2, but I could ask you like 18 or something which is not a multiple of 2 or that is not an exponent of 2. So you could do this by knowing the exponents of 2. So 18 is between 16 and 32. So you're doing a floor here. So log 18 to the base 2 is 4. So it is 4,000 times 4, which is 16,000 bits per second. Okay? Now, why can't there be channels of infinite bandwidth? So again, if you see here, each time slot has to be for a finite time period. You cannot have a zero time, the time slot of duration 0, right? So each time slot has to be for a finite positive quantity. So which means the baud rate is kind of a finite quantity, it cannot be infinite, right? So that's why, since and we know that the bit rate is baud rate times log k to the base 2, and the baud rate is a finite quantity, the bit rate also has to be a finite quantity. Also, the larger the number of signal levels, okay, the more difficult it is and error prone it is at the receiver side to decode the data from the signal because signals deteriorate with distance. So if you use too many voltage levels, it may be you may have a situation where you may not be able to differentiate one voltage level from another voltage level at the receiver side. Okay, so because of these two reasons, we cannot have channels of infinite bandwidth. Now draw the waveform diagram to send the bit pattern for this particular bit sequence using the RS-232 standard matches to encoding standard. Let me go over what we have here. For the RS-232 standard, we need to have a start bit and a stop bit. So we will also need to encode the bits in terms of these two voltage levels. So we use negative 15 to send bit 1 and plus 15 to send bit 0. And initially the channel is considered to be idle and is represented using negative 15 volts. So if you want to indicate the starting of a transmission, you want to use send a start bit. So we send plus 15 volts for a particular time slot, which the sender you have to agree, and then you send a byte or whatever the unit of data that you want to send. Here's a byte, and we send one bit 1 is represented as negative 15, and another bit 1 again negative 15. You don't need to actually draw this dotted line. This is just to indicate the duration of the time slots. And then the 0, you send bit plus 15 volts, and then 1 negative 15, another 1 negative 15, 0 plus 15 volts, and so on. Now to indicate the stop bit, you send negative 15 volts because the start bit is plus 15, and then you don't have anything else to send, and keep the channel idle by continuing to maintain it at negative 15 volts. Now if you want to send the things using the Manchester encoding standard, uh, so let's say you want to send this. So in Manchester encoding, a transition from a positive to a negative voltage level is considered as sending bit 0, and a transition from a negative to a positive voltage level is considered as sending bit 1. So if you want to send this bit sequence, then you send this 0 from positive to negative, and then negative to positive for 1, then positive to negative for 0, and again at immediate a kind of what you call on and the beginning of this time slot, you go back to positive. Again, you can send a 0, and again for a 1, you go from negative to positive, and again you want to send a 1. So have the transition right there at this time slot. Again, go from 1 negative to positive. Again, you want to send a 1. So immediately bring the voltage level down to negative voltage level, and again do a transition from negative to positive. Then you want to send a 0, so do a transition from positive to negative. Okay. With respect to the encoding criterion, what's the difference between the two standards? So the RS-232 standard uses the discrete voltage levels as the means of representing the encoding of bits, zeros and ones, whereas here we use a transition of the voltage level from one level to another level as to encode bits 0 and 1. Okay, so there a finite a discrete voltage level like plus 15 or negative 15 volts captured or encoded the transmission of bits 0 and 1. As here the transition from a positive to negative for bit 0 and from a negative to positive voltage level for bit 1. So now let's do delay calculations. We have here, so the transmission delay is the packet size or channel bandwidth. Propagation delay is the channel length divided by speed of the signal on the channel. So here I gave you the number of characters that you want to send using RS-232 standard and the channel bandwidth and all those things. So note that in an exam I could explicitly tell you to assume a character is this many bits. So I could say assume a character is 8 bits, then you have to use a character as 8 bits. Like in this example, you can use a character as 7 bits here because printable characters are 7 bits, are represented using 7 bits. So if I tell you explicitly to use a certain number of bits per character, go ahead and use whatever I tell you. Otherwise, you can use like what I have here, 7 data bits per character. Now, also, if you use RS-232 standard, we have a start bit and a stop bit, right? So, in this case, since you're sending 7 bits per character, you have to also consider the one start bit and one stop bit. So, we have totally 9 bits, okay, per character that you want to send. Okay, 7 plus 1 start and 1 stop bit. So we want to send 2000 characters. So the total number of bits you'll be sending is 2000 times 9, which is 18,000 bits. Now the transmission delay is the data size, which is 18,000 bits divided by the channel bandwidth, which is 40,000 bits per second. So if we do the math, 18,000 over 40,000, make sure the units are consistent. It is bits here and bits per second here. So it's 0.45 seconds. Now the propagation delay is the channel length over the speed of the signal on the channel. So the channel length is given as 2 times 10 to the 6 meters divided by the speed of the signal on the channel. So the speed of light is 3 times 10 to the 8 meters per second. So I have given you, assume the speed of the signal is 60% of the speed of light. So the speed of the signal is 0.6 times 3 times 10 to the 8. So if you do the math for this, you'll get 0.011 seconds. So the total delay is the transmission delay plus the propagation delay. Okay. Now, if you want to transmit these guys, we have this AND case. So what is little Indian transmission? Little Indian means you're going to send the least significant bit first, or in the case of a byte, you're going to send the least significant byte first. Big Indian means you're going to send the most significant bit first, or the most significant byte first, depending on this a byte level or byte level. Okay. So in a bit, sorry, in a byte, so if you write, for example, ASCII value 65 in binary, okay, so this is 65 in binary. So this, in terms of the weights for the bits, so these are the weights for the bits. So we call this bit as the least significant bit because it has a least weight, whereas this bit is the most significant bit because it has the maximum weight possible for that byte, right? So it's 128. So when I want to send this byte in, say, the big endian transmission, I'll send this bit first, right? So within this byte, if I want to send the bits in big endian transmission order, then you will send the 0 first. As if I want to send the bits in the little endian order, then I would send this 1 first. Okay, so now you want to send these um, characters, right? So I have, say, and here, A and T. So in a word like and, the first character is the most significant character because that's what you want to send first, right? And the last character that you want to send can be treated as the least significant character. So if you want to transmit the characters or the bytes, each character can be assumed as a byte here. In the big Indian transmission, then send, so if you have, say, for example, so bytes in big Indian, if you want to send A and T, you send A first. Okay. If you want to send the bytes in little Indian order, you send T first because that's the least significant character. Okay. So in this example, you have bytes sent in little Indian order. So T is sent first, and then N, and then A, and the bits within a byte are sent in big Indian order. So which means within a byte, we want to send the bits in big Indian, which means the big guy goes first, the most significant bit goes first. So that's why you have 1, 2, 3, so on up to 8. Okay? And then again within this byte you send the most significant bit first, so you send this bit first, followed and so on up to this bit. And then you again send this within this byte the most significant bit first, so starting from here all the way to this one. Okay. Now we want to send the other way, the bytes in big Indian and the bits in little Indian. So bytes big Indian means you send the first character A first, right? So you send, now within the byte, you send the bits in little endian order. So you send the least significant bit first. So you send this one first, so on, and then within a byte again this one first, and so on, and then this one. Okay. So the bits are sent in little endian order. So you can have the other two combinations also, bytes in big endian and bits as well as in big endian, and then bytes in little endian and the bits also in little endian. Okay. So you can do that. Now this is for amplitude modulation. Here I have given you a bit sequence and asked you to use 4 amplitude levels. So if I ask you to use 4 amplitude levels, then you could use something like this. You could come up with your own mapping. So I suggest using this one because we have 4 wide equally spaced amplitude levels, A over 8, 1 8, 3 8, 5 8, 7 8 of the amplitude. So if I want to send, like I want to send here, actually this should correspond to 0 1, right? So 0 1 is 3/8 of the amplitude. So this is 3/8 on cycle. Then I want to send 1 0, right? Those are the next two bits, 1 0. So if I want to send 1 0, I have to use 5/8 of the amplitude. So this is 5/8 of the amplitude. Then I want to send 0 1. So to send 0 1, I have to use again 3/8 of the amplitude. So that is one cycle. Then 1 1, I have to use 7/8 of the amplitude. Okay. So that is amplitude modulation. So now we have frequency modulation. So I want to send this bit sequence, including some idle channel. So I use 2 cycles to represent idle, and then 2 cycles per unit time, and then 1 cycle to represent bit 1, and 3 cycles to represent bit 0. So I want to send 0, so I have 3 cycles within a time unit, and then bit 1, so you have 1 cycle, then idle, so 2 cycles, and then again a 1, so 1 cycle, again idle, 2 cycles, and again I want to send 0, so I have 3 cycles. Okay. So you fix a time unit, and then within the time you play with the number of cycles you want to send. So 2 cycles for idle, then 1 less cycle bit 1, and then 1 more cycle than idle, 3 cycles for bit 0. Then phase modulation. So again, I give you the bit sequence. You need to use the number of phase shifts. So here I have to use 2 phase shifts. So use 502 for bit 0, 3502 for bit 1. So one full cycle is 2 pi. So 1/4 of a cycle is 502. Okay. So I want to send bit 1, so I need to cut 3/4 of the cycle, and I send only the last quarter. Then for bit 0, I cut only 1/4 of the cycle because it's 502, and I send the remaining 3/4. Then for bit 1, again I cut last 3/4 and just send, sorry, the first 3/4 and send the last quarter like this. Then the channel is idle, so I send the whole signal. Okay. So if I now want to again send bit 1, I cut the first 3/4 and send only the last quarter, this portion for bit 1. Then again the channel is idle. Now I want to send bit 0. I cut the first quarter and send the remaining part of the cycle. Then the channel is idle. Then I want to send again bit 1. I cut the first 3/4 and send only the last quarter here because it's 3 pi over 2. So for pi over 2, basically, um, just simplify like this. Pi over 2 is you cut first quarter and send the remaining 3/4. Then 3 pi over 2, cut the 3/4, cut the first 3/4 and send the last quarter. Okay. All right, so difference between baseband and broadband technologies. So baseband, you can have only one signal that can be used at any point of time. So if you have multiple user pairs that want to use the channel, you have to share among them. Okay, so only of course one user pair can only use the channel at any point of time. So you have to do some kind of time division multiplexing or like statistical multiplexing where we can alternate between the different users. Whereas broadband is where you have multiple signals that are available over there, each signal, of course, traveling on different frequency. So you can typically allocate one frequency for each user pair, so that is frequency division multiplexing. Or if you want to optimize this, you can assign more than one frequency depending on the active users. So if there's an active user who needs more frequencies, you allocate more frequency for that user. Okay? All right. So what's the advantage of statistical multiplexing over time division and frequencies? Both time division and frequency are both static in nature because in time division multiplexing, once you assign the time slot to the different streams, you cannot really use a time slot for one stream if that stream needs the time slot. So for example, if streams 1, 2, 3, 4, 5 are using these respective time slots. But if these, say 2, 3, 4, and 5 don't have anything to send, the channel remains idle during those time slots. Whereas if stream 1 has anything to send or more information to send, it has to basically wait for the subsequent time slots to come for its own slots. Like stream 1 can send only this time slots and as well as only in this time slot. It cannot send in the other time slots. Same thing with frequency division multiplexing. If different user pairs are assigned the different frequencies, then a user pair can use only that particular frequency. They cannot use the other frequencies. So this is static allocation, whereas um, statistical multiplexing is more dynamic. The users are assigned a channel on a first in first out basis in the sense that if you consider this as a time axis and indicating the order in which the packets are coming, so this packet is scheduled first and then this one and then this and then this and so on. So the user pairs or the streams are given access to the channel depending on the order in which the packets are received from them. Okay? Actually, I'm sorry, I had to consider in this order. So this is the first packet, so this is one, and this is the second one, this is the next packet, and this is the next packet, and this is the brown next packet, and this one. Okay, right. So packets are considered increasing order of the time in which they come. Right? Okay. So then let's do this problem on time division multiplexing. So you have two computers that want to send 1 megabyte of a file, and each packet is of size 512 bytes. The channel bandwidth is 40,000 bits per second. The hardware switching delay from one user to the other user is 10 milliseconds. Okay, so you have again here the two users who want to use a chat channel. The channel bandwidth is given as 40,000 bits per second and packet size is 512 bytes. So your first task is to actually find the transmission delay per packet, how long it would take for each user to send the data, a particular packet. So the transmission delay per packet is the packet size or the bandwidth. So packet size is 512 bytes divided by bandwidth, which is 40,000 bits per second. So we have to convert the bytes to bits. 1 byte is 8 bits. So 512 times 8 divided by 40,000 bits per second. So it's 0.1024 seconds. The hardware switching delay is given as 10 milliseconds, which is 0.01 seconds. So for one particular user, the transmission delay is 0.1024 plus hardware switching delay is 0.1124. Why we do that? Because we can now have a timeline where you send from A and then you switch to B and then you have B send a packet and then you switch to A, have A send a packet and then switch again to B and so on. So we can consider now one epoch is where A sends, then this is switch to B, B sends, then switch to A, right? So this is one epoch. So you can say it is 0.1124 for A and then a switch to B and then another 0.1124 for B to send and including a switch to A, right? So the total time that an epoch runs or one turn runs is the sum of these two, which is 0.2248. So now we want to also find the number of packets that each machine needs to send. You're given the file size, which is 1 megabyte. So 1 megabyte is 1024 kilobytes. So 1024 kilobyte, right? So 1 megabyte is 1024 kilobyte. 1 kilobyte is 1024 bytes. So you have 1 megabyte is basically 1024 times 1024 bytes. Okay, and the packet size is 512 bytes per packet. So if you do the math, you get 2048 packets. So the delay to transfer the whole file per machine is 2048 times the time it takes for one epoch, which is 0.2248. So it is 460 seconds. Okay. Then let's do this CDMA. So here each we want to send using the same signal. So each user is given a chip sequence and we want to send data using those chip sequences. So the first condition you have to check is make sure is the chip sequence is given to you are orthogonal to each other. So how we check for orthogonal property is replace all the zeros in order to do the math. We'll replace all the zeros with -1. So you're given this chip sequence. So the initial step is to take dot product of the two chip sequences. So for user 1, the chip sequence C1 is given as 0, 1. So it is -1, 1. For user 2, the chip sequence is given as 1, 1. So it is 1, 1. So if you take the dot product, it is the pairwise multiplication. So -1 times this 1, this plus this 1 times this 1, which is this. So -1 plus 1 is 0. So the only the dot product is 0, we can see the two chip sequences are orthogonal. So now let's see how we do the encoding at center 1. So to encode, what we do is we take a product, matrix multiplication, where you have the transpose of the chip sequence. The chip sequence is written like this, row-wise, -1, 1. So you want to take a transpose of this. So if you transpose this -1, 1, you get -1, 1 column-wise. So it's now a 2 row 1 column matrix, and then you have the data that you want to send, which is given by 0 1 1 0. So if you replace all the zeros with the -1s, it is something like this. So you have this is your data. So now we want to send this is a 1 by 4 1 row 4 column matrix. So you do the matrix multiplication. So you have a 2 by 1 matrix multiplied with the 1 by 4 matrix. So the product is going to be a 2 by 4 matrix. So you multiply, so to get the row, right, the first row, you fix the first row in the first matrix and multiply with each of the columns. So first row, -1 multiplied with -1 is 1, and then -1 multiplied with 1 is -1. -1 multiplied with this 1 is -1. And -1 multiplied with -1 is a 1 here. Okay, so we fill the first row by fixing the first row in the first matrix and multiplying that with each of the columns. Similarly, fix the second row in the first matrix to fill up the second row here, fix the second row here and multiply with each of the columns. So 1 times -1 is a -1, 1 times 1 is a 1, 1 times a 1 here is a 1, and 1 times a -1 here is a -1. Okay. Then let's do the same thing for sender 2. The shape sequence is 1, 1. So you take a transpose of this. This is the data sender 2 wanted to send. So it is this 1 multiplied with each of this. So it is same as that. Then this 1 multiplied with each of this. So it is same as this. So now we want to send the composite signal from these two senders. So S is equal to S1 plus S2. So basically now this is a matrix addition. So we do pairwise addition again. So 1 plus this 1 is going to be 2. Then negative 1 plus this negative 1 is going to be negative 2. Then negative 1 plus this 1 is going to be 0. Then 1 plus negative 1 is going to be a 0. Similarly, negative 1 plus 1 is a 0. 1 plus negative 1 is a 0, and so on. Okay? So now the receiver needs to retrieve the data. So the receiver for S1 needs to apply the chip sequence for S1. For S1, the chip sequence is this, right? So negative 1, 1, that's the chip sequence for sender 1. So now we don't take a transpose, multiply as it is, because as it is a 1 row, 2 column matrix, and this is a 2 row, 4 column matrix. So the product is going to be a 1 row, 4 column matrix. So if you want to get this row, fix the row, the first matrix, and multiply with each of the columns. So this is negative 1 times 2 plus 1 times 0. So negative 1 times 2 is negative 2 plus a 0, so it's negative 2. The negative 1 times negative 2 is a 2 plus 1 times 0 is a 0, so that's why you have a 2 here. Then negative 1 times 0 is a 0 plus 1 times 2 is going to be a 2. And then negative 1 times 0 is a 0 plus 1 times negative 2 is a negative 2. So if you notice here, you will get only 2's and negative 2's. So now you can divide this by 2 because we have 2 users associated here to send. So it is negative 1, 1, negative 1. Then now replace all your negative 1's with zeros. So you have the data that sender 1 wanted to send. Okay. Even in a composite signal, as I said before, you will have to have only 2's, negative 2's, and 0. If you have anywhere a 1 or negative 1, it means you have made a mistake because we are using 2 users here, right? So to send data, so the composite signal should be either 2, negative 2, or 0, some variant, some one or more of these, like we see in this case. Okay. Similarly, the receiver for our S2, we'll use a chip sequence for S2, which is 1, 1, and multiply with the matrix we have here, the composite signal. So 1, 1. So 1 times 2 is a 2 plus 1 times 0, so it is a 2. Then 1 times negative 2 is a negative 2 plus 1 times 0 is negative 2. Then 1 times 0 is 0 plus 1 times 2 is a 2. Then 1 times 0 is a 0. Then 1 times negative 2 is a negative 2. So again divide by 2, we have 1, negative 1, 1, negative 1. So that is 1, 0, 1, 0. Okay. So we'll stop here.